So, have you ever wondered how a physicist actually sees the world? It's like they have a secret language to describe everything from a falling apple to the entire universe. And today, we're going to learn 3 of the most important words in that language: work, energy, and power. Let's dive right in.
First up, a word you definitely think you know: work. I mean, we use it all the time for pretty much any kind of effort. But for a physicist, work means something incredibly specific. And honestly, the definition might surprise you.
All right, take a look at these 2 pictures. On the left, you've got a boy pushing a car, and hey, it's actually moving. On the right, a man is pushing against a solid brick wall with all his might, but that thing isn't budging. Now, both of them are using force. Both are probably going to get tired, but are they both doing work?
So, what do you think? Is it the boy? The man? Maybe both. There's a secret rule that physicists use to decide, and we're about to find out what it is. And there you have it. The answer is the boy pushing the car. Why? Because in physics, for work to actually happen, 2 things absolutely must take place. A force has to be applied, and that force has to make the object move.
So that guy pushing the wall, no matter how hard he pushes, no matter how much he sweats, he is doing zero scientific work. The wall didn't move an inch. The rule is simple and strict. No displacement equals 0 work. End of story. And of course, this whole idea boils down to a really beautiful and simple formula. Work is just the force you apply multiplied by the distance the object moves. That's it. That's the core of it all.
Now here's where it gets even a little weirder. Check out this other case where work is 0. Imagine a porter carrying a heavy suitcase on his head and walking forward. Okay, he's applying a force, right? He's pushing up on the suitcase to keep it from falling. But he's moving forward. Because his force is at a 90-degree angle to his direction of motion, physics says he's doing absolutely 0 work on that suitcase. Wild, right?
Okay, so if work is the action, the results of moving something, what is it that you need to do the work in the first place? Well, that brings us to our second key concept: energy.
You know, the easiest way to think about energy is to think of it as the capacity to do work. It's kind of like the currency of the universe. If you want to make a transaction happen, like doing work, you've got to spend some energy.
Now, this energy currency comes in 2 main flavors, especially when we're talking about things that move. There's potential energy, which is stored up, and there's kinetic energy, which is the energy of motion itself.
So let's break that down. Potential energy is energy that's just waiting to happen. It's the energy packed into a stretched bowstring, or stored in a rock that's sitting at the very top of a hill. Kinetic energy is what happens when you let that potential go. It's the arrow flying through the air or that rock tumbling down the hill. One is stored and the other is active. Okay, so we've got work, which is the task, and energy, which is the currency you need to do it. But there's one last piece of the puzzle here: power. And this isn't about how much currency you spend. It's about how fast you spend it.
Power is all about time. It's simply the rate at which you do work, or how fast you transfer energy. If you do the exact same job but you do it faster, you are using more power.
Let's go back to our porter. Imagine 2 of them lift the exact same heavy load up to the same roof. Okay, they've done the exact same amount of work. But what if one of them does it in 1 minute and the other takes 2 minutes? Well, the first guy is twice as powerful because he did the same work in half the time. Same work, completely different power. So we've looked at work, energy, and power. Now it's time to bring it all home and tie them together with one of the most fundamental, most beautiful rules in all of physics. This is a principle that governs, well, everything in the known universe.
This right here is the principle of conservation of energy, and it's a law that cannot be broken. You can't just make energy out of thin air, and you can't make it disappear. All it ever does is change form.
So, going back to our currency idea, this means the total amount of energy money in the entire universe is fixed. It's a closed system. All that's ever happening is that this currency is getting exchanged and converted from one form to another.
And you see this happening literally everywhere, all the time. A battery turns chemical energy into electrical energy. A candle turns chemical energy into light and heat. A dynamo spins and turns the mechanical energy of motion into electricity. It's a constant transformation.
But, you know, talking about it is one thing. The real magic is seeing this law in action. So let's put it to the test with a simple, classic physics experiment.
We're going to track the energy of an object as it falls from a height. We're going to watch its stored potential energy and its active kinetic energy, and we'll see if that total amount really truly stays the same.
Okay, this graph right here, this is the proof. It's tracking the two types of energy as an object falls. The blue line is its potential energy, the red line is its kinetic energy, and that flat line at the top is the total energy. Just watch what happens.
See that? As the object falls, its height gets lower, so its potential energy, that blue line, goes down. But at the exact same time, it's speeding up, so its kinetic energy, the red line, is going up. They're a perfect mirror image of each other. And the whole time, look at that line on top, the total energy. It's perfectly flat. It doesn't change at all.
This is it. This is the law of conservation in beautiful graphical action. The stored energy it had at the top gets converted bit by perfect bit into the energy of motion on the way down. The currency is just being exchanged from one account to another. Not a single penny is lost.
And that brings us to one last big question. We all know a bouncing ball eventually stops bouncing. But if energy can't be created or destroyed, then where did it go? It didn't just vanish. Now that's a puzzle for another time, but it just goes to show how deep these simple rules really are.